Hi, everyone. This is Aaron Larson, executive editor of Power Magazine, and you're listening to the Power Podcast. On today's episode, I'm joined by Carlos Araque. He is the CEO of Quaise Energy. Carlos, thanks for joining me. And if you don't mind, please tell a little bit about your company and what you guys are focused on.
Thanks for having me, Aaron. I appreciate the opportunity. So Quaise is trying to unlock geothermal at a global scale. We're trying to make geothermal a key element of the energy transition. And that to us means terawatts, thousands of gigawatts of clean energy, no matter where you are in the world. The company is born out of MIT's technology. A lot of the team is actually coming from oil and field industry, veterans of that industry, and we're really trying to dig deeper than ever before possible. I think if we can do that, we change geothermal and we change the energy transition.
Yeah, I know I've covered geothermal in several articles and talked about deep dry rock geothermal. Can you explain how the deeper geothermal differs from what is more conventional and in use today? Can you kind of explain the differences and why that's important?
Yes, gladly. So most of the geothermal that you see today is hydrothermal geothermal. That means there's an aquifer in place, there's water down there, which is hot, and then we extract that water, which comes out as vapor for the most part, and we run turbines or we run a organic binary cycle plant. So that's most of the geothermal you see today is actually that. There's another big part of that, which is we directly use the water, the hot water. We don't make electricity out of it. We just run it through pipes and we heat spaces with it. That's direct use. So the common denominator there is that you have water down there and you extract this water. So enhanced or engineered geothermal systems are a different category emerging from the 70s, 1970s onwards, which is you don't worry about water. Forget about water being there. You just look for hot rock. And for the most part, this hot rock is dry. We just simply drill to it. We create permeability. We run water through it, and we extract the water that we ran through it and do as we used to before. We're taking that concept a little bit further in temperature. We think that when we can go not only to 100 degrees centigrades, but 300, 400, or even 500 degrees centigrade, you can do amazing things, like repowering a fossil fire power plant with clean energy in a very short time frame. So that's the key difference. We're going for hotter rock because we want our water to get hotter. We want it even to be supercritical, which is the fourth state of the phase, the fourth phase of water when it goes above a certain temperature and pressure. That's what we're looking for.
If I understand it correctly, this is pretty much available everywhere around the earth. It doesn't have to be in specific locations. Like a lot of times in today's use of geothermal, you have to be in places like Iceland or in California. There's a lot of geothermal in use. But this type of deep dry rock geothermal is available everywhere. You just have to go down deep enough to find it, up to 10 miles or 12 miles deep. Is that correct?
That is correct. Yeah. So our goal really is to go for the temperature more than the depth. The depth just happens to be a consequence of where you are on the planet. So if you're in Iceland and you want to get to 400 or 500 degrees centigrade rock, I mean, you drill anywhere from, 3 to 5 miles and you're there. But if you're not in Iceland, to get to that same temperature, you have to go a little bit deeper. So that's the key. We're going for the temperature, and then we'll be able to drill as deep as necessary, no matter where you are in the world, to be able to get to those temperatures. We want to be able to make geothermal independent from the typical places you associate with geothermal, like Iceland, Italy, Japan, Mexico, Philippines. We want geothermal to be viable no matter where you are in the world. And for that, you need to go deeper. 20 kilometers, 12 miles will pretty much get you 95% of the population of the world.
From what I understand, the footprint for this type of a system would be relatively small compared to other types of renewable energy. For instance, a wind farm requires much more space. A solar farm would require much more space, whereas these wells can be drilled in relatively small footprint.
Yeah, that's a very important aspect. The best person that speaks of this is Vaclav Smil. Vaclav Smil. He talks about power density, the concept of power density. It's how much power can we get per square meter or square kilometer or square mile of space of land. To give you an idea, fossil fuels give you around 1,000 watts per meter square. Solar gives you about 10, and wind gives you about 1. So from a land utilization perspective, every unit of energy that you get from fossil fuels takes up 100th to 1,000th of the space that wind and solar do. We're trying to make geothermal as power dense as fossil fuels. That's another reason why we're looking for these temperatures. When you do that, the footprint per unit of energy from geothermal can be 100 to 1,000 times smaller than the footprint for the equivalent in wind and solar, but clean, equally clean. So that makes a big difference. When you're talking about the energy transition being about terawatts of energy, we find serious constraints with land utilization in wind and solar. We basically start using land so much to replace fossil fuels with wind and solar that we get into other ecological trouble. So we got to be careful with that. We cannot save the atmosphere by sacrificing the land and the ecological spaces on land. Geothermal actually fits both, as power dense as fossil fuels, as clean as wind and solar.
So what are the challenges to getting down to these depths into the earth? I mean, the drilling, I assume, is what's holding us back at this moment in time. Can you explain how that's changing and how you're developing new technology to make it actually viable?
That is correct, Aaron. So the drilling is the key bottleneck right now. I come from oil and gas. I understand drilling fairly well within the context of oil and gas. And it really boils down to temperature. To drill, the state of the art of drilling technology is in the 200 degrees centigrade neighborhood. And the reason for that is the electronics that go with the drilling systems. Making higher temperature electronics is a very, very difficult task. So that's what's holding it back. There's other reasons. The hotter you go, the more you have to change your drill bits because they wear faster. So if you imagine drilling at 5 kilometers below the surface of the earth, and your drill bit will only last you a few hours because the rock is so hot and so hard, pulling that drill string out of the hole so that you can change the drill bit and pushing it back in into the hole can look like a wick in between in and out. So a wick to pull out of the hole, a few hours to change the drill bit, a wick to push down into the hole to drill a few more hours. It becomes exponentially impossible to do that. And if you look at some of the deeper holes we've drilled as humans, it's taken us decades to do them. The Kola borehole in Russia took 20 years, close to. The KTV in Germany took 5 years or so. So what we're trying to do is to do away with electronics down the hole and drill bits. We don't want drill bits. We don't want anything wearing, anything having to be changed. And that's where the drilling technology that we're proposing comes into play. We're basically trying to do energy drilling, directed energy drilling with millimeter waves. To give you a very, very quick idea, imagine a microwave source on the surface. It's called a gyrotron. We beam this energy through a pipe into the hole. Together with this energy, we push a gas, could be nitrogen, could be air, could be argon if necessary. And at the bottom of that pipe, this energy comes out, evaporates the rock, and the gas picks up the vapor of that rock and pulls it back up. What comes out of the hole looks like volcanic ash, and the hole actually burns its way down, 5, 6, 10, 15, 20 kilometers as needed to get to the temperatures we're looking for.
And so is this actually achievable today with the technology that you have, or are there things that still need to be done to make this feasible?
So we think it's doable. Let's put it this way. From 2007 to 2017, 10 years, Dr. Paul Waskov at MIT did a lot of work to show that the fundamental physical understanding is there to do this. So we think it can be done. Now, the challenge, and this is what we're doing now as a company, is scaling this up. How do we go from a lab benchtop prototype to a lab warehouse type prototype to the field, to a 1 kilometer hole, to a 10-kilometer hole? There's a very natural progression as we go there. And that's why Quaise was created, to take the proof of concept in the lab and scale it to the field. That's very much where we find ourselves right now. Over the next 3 years, we're going to be working with key people in the oil and gas industry. One of them is one of the largest drilling contractors in the oil and gas industry. And hand in hand, working with them to actually show that this is not only a good idea, but it's actually a viable idea. We're going to be doing this in the Western continent, in the Western United States.
And when do you expect to begin that project? Is that something that you're still getting developed or getting approval for, or is that something that's actually in the works?
So I consider the project as started already, right? We are doing permitting, we're looking at regulation, we're designing this operation and this system together with our drilling partner. When do we actually go in the ground to start doing a drilling demonstration? Is going to be in 2024. So 3 years from now. That's when we go there together, having done all of the preparation work, all of the permitting work, all of the regulation compliance work, and actually start drilling and actually start showing that we can burn through these very hot and very hard rock.
Once it's proven and you have the concept, will it be economical? Is it still going to require some scaling or some other technology to make it actually economical to do in large scale?
So we believe so. We are targeting, and we believe we can get to $1,000 per meter drill. Sounds like a lot, but in the perspective of these operations, it's actually very competitive. So if we can drill for $1,000 per meter, we can get to these temperatures, and we can create permeability, doing enhanced or engineered geothermal systems. Then we can basically make a geothermal asset that looks like 3 wells, 1 injector, 2 producers, producing 100 megawatts of thermal energy, or producing 50 to 60 megawatts of electric energy. When you put all of these things together and do a financial model over these things, you realize that you can land electricity in the $10 to $30 per megawatt hour. That's 1 to 3 cents per kilowatt hour. This is better in many cases than wind and solar, without the subsidies and without the externalities of land use and material utilization. So that's a big part of what we're trying to show, that we can get to $1,000 per meter, because if we can do that, that's where our electricity will come in. The rest is easy. The rest is creating permeability. I shouldn't say easy. It's done. People do it. We know how to do it. And building a power plant of that geothermal asset is something that can be done. So we worry less about hard developments on those areas, because I think the bottleneck really is the drilling technology. If you can crack that, everything else falls in place.
And how long would a plant like this be viable? I mean, would it last for 50 years or longer, or are there constraints along the way, where it might only be serviceable for 20 years or less?
We designed these systems to last 30 years at a minimum. So we want to build a power plant and a geothermal field around that power plant that will give us a depreciation schedule over 30 years at the very minimum. Now, these plants in practice, in reality, they actually last much, much longer. You will have no hard time finding geothermal systems that have been going on for 100 years. So we think they'll go there. But one of the key things that will deteriorate their performance over time is something called temperature drawdown. Right? The temperature in the rock will decrease because we're extracting thermal energy. Not by a lot, we're talking about a few degrees over decades, but enough for the asset to perform at a lower performance that it was originally designed for. So at some point, what you might have to do is drill additional wells to compensate for that thermal drawdown, or move on to a different site, leave that one alone, let it recharge because geothermal is renewable, it recharges itself, and then come back to it. But we're talking about decades. We're talking about very durable, very reliable, clean energy systems.
If I understand it correctly, you've been working with the Department of Energy in their Advanced Research Projects Agency. Can you talk a little bit about that? Have you gotten any money from them to help with the project?
Yes, we have. So the company, half of the money that we currently have, about $5 million, comes from the Department of Energy. It was a grant we obtained in 2019, and it's very much about helping us move quickly and with little capital early on, right? So if you imagine a startup company doesn't have a lot of resources, right? Doesn't have the luxury of being able to buy large capital assets like a gyrotron or a high power system. So we instead, with that money, leverage facilities that already exist in the national labs, and we actually proof the concept at a larger scale through that mechanism. So that's what we're doing. But that's only technology demonstration, right? Then we have to make a product. We have to design an operation and take it to the field. That we do outside of that money. We get an equivalent amount of money from private venture capital funds, and we use that to advance the product and the operational mission of the company, as opposed to the technology mission, which we advance with the ARPA-E funds.
So for the company Quaise, for example, what's your business strategy once the technology is proven? Would you then be building plants for power companies, or would you just license this to the somebody else to do actual construction of these plants and scale up?
So we, in the fullness of time, right, we seek to very compelling business models. The first one is as brownfield developers. And brownfield is a term I borrow from oil and gas. It basically means you already have something in place and you are using your technology to make it better. So in this case, what we intend to do is go to existing power plants. It could be a coal power plant, it could be a gas power plant, any of the thousands of fossil-fired power plants that exist in the United States and around the world. And we will propose to them to create a small geothermal field around them, which is matched to the turbine specification of the power plant. What comes out of the ground is steam that feeds into the turbine, and the rest is what they've always done. The turbine creates electricity, the plant is already connected to the grid. So imagine that. Imagine you go to a 500 megawatt power plant, and within 3, 4, 5 months, you actually make it clean. This is unparalleled by any other form of clean energy. There's nothing that can leverage existing infrastructure quite like that. So that is the most compelling and the first business model for us. We want to develop geothermal fields around power plants, and we want to repower them with clean geothermal steam. The second one is a greenfield development, which means we do everything from scratch. We create a geothermal field, we build a power plant, we commission that, it produces and interconnects to the grid and produces electricity into the grid. That takes longer because you have to build a power plant, but we'll certainly do that as well. In the end, we want to sell energy. We don't want to sell services, drilling services, because we think energy is what the world needs. And we're short by terawatts. So that's what we're going to build our value proposition around. We might do licensing to other industries like mining or civil construction, but those are different use cases of the technology. For energy, we are an energy company, not a drilling company. Drilling is just the uniquely differentiated technology to be the best and the most valuable geothermal company ever.
That's interesting. So you think that if you did get it to this level where you go to an existing power plant that may be closing down, you could actually drill these wells within a 3 to 5 month period? Do you think that's possible?
I think that is possible. You know, if you think about what the oil industry was doing in the shale revolution of the 2010s, they were drilling 30 to 50,000 wells in the United States alone per year. I mean, the sheer capacity of that industry is incredible. We take it for granted, but it's taken 100 years to develop. So now we're going to borrow from that and use that might, that industrial might, to do something much smaller and repower power plants. That's what we want to do. We want to be able to put gigawatts, tens of gigawatts, hundreds of gigawatts even, into the grid in months, every year. That's what the energy transition needs. And that's what I think geothermal is very uniquely positioned to do when you do geothermal this way. We're not happy with megawatts. We need terawatts on the grid around the world. That's energy transition.
And would the steam that comes out of these wells then have to go through some sort of a reboiling process, or would it actually be clean enough and pure enough that you could run it straight into a turbine?
So these are not fluids that were in the rock. So it's water that we put in. These are enhanced geothermal systems. So we think that what comes back to a great extent is quite usable as it is. You always pick up things along the way, and you always need to do some minimal processing. But this is very different from today, trying to extract fluids that were down there, you know, for hundreds or thousands of years, and then running them through a turbine. That requires very heavy processing. So because we're using enhanced geothermal systems with fluids that were not in the rock to begin with, we think those fluids, when they come back, will be way, way cleaner and will require much, much less processing. So you push it into the ground, it comes back out from another well, you feed it to the turbine with minimum processing. You make energy, you repeat the process.
Well, it sounds almost too good to be true, but I hope it's successful, and I hope that it works out. You know, you've answered most of my questions. Is there anything else you'd like to bring up before we close up the podcast?
No, I think it's simply the point, emphasizing the point that, you know, the energy transition is a monumental challenge to humanity. Wind and solar will play a big, big part, but you're starting to see it. We need other solutions that don't exist today. I think geothermal is not getting attention. I think it can be one of the most compelling ones. So I encourage anybody to take a closer look at what geothermal can actually do and to reach out to me. You know, go to the website, www.quaise.energy, and in the form, just leave your name, and we're happy to read and correspond and communicate. You know, a big part of our work is evangelizing and showing people that we need to think better and higher of geothermal, because it's one of the very few solutions that can actually help us truly transition energy away from fossil fuels.
All right. Well, thank you, Carlos, and I appreciate it. And to just give the audience a little bit of clarity, Quaise is spelled Quaise, and it's .energy. Is that correct?
That is correct. That's it.
Okay. Well, again, thank you, Carlos, for your time and for explaining the work that you're doing. And I wish you all the success in the world.
Thank you, Aaron, and thanks for the opportunity to talk to everybody out there.